want it to go anywhere.
Okay. Okay, so one more time, let me say that again. So what we've got here is graphed in blue is the original function, f of x equals x squared plus 3. Graphed in red is the what we found to be the derivative function, which was 2x. Okay, now what was the meaning, did we say, of the derivative function, going back to last Thursday/Friday?
Rate of change.
It's a rate of change, right? It's the instantaneous rate of change, or the instantaneous slope of the function, right? And so that's what we would use to calculate, what we did use to calculate the equation of a line tangent to a curve at a point, right? Okay, here's where I want you to make this connection though, between these two functions. This is really cool. Okay, so the blue function is the original function, the red function is the derivative, right? You just told me that the job of the derivative function is to calculate the slope of the curve for any value of x we choose, right? Slope of the curve is equivalent to the slope of a line tangent to the curve at that point. Because remember, if we zoom in infinitely far, the curvature disappears, right? And the function starts to look flat. And so in that instance, the tangent line and the curve are identical, right? Okay. Well, on that blue function, where is the slope equal to 0? The slope of the function? At what point?
0.
At 0, 3, isn't it? Right? That's the place where the tangent line would be flat, correct? Okay. What's the slope of the function at x equals 1? Well, it looks like at x equals 1, it's sloped up a little bit. I mean, it's positive, right? At x equals negative 1, it's negative, correct? Okay. Can you make a connection between the value of the red function and the slope of the blue function at any point?
0.14 is the same. At 0.15 is the same. No.
Okay, but yeah, I don't care about anything numerical here. I just want to know, can you see a connection between the shape of the red function and the shape of the blue function? Remember, the red function is the graph of the derivative, right?
Because the right side of the red is your positive, the right side of the problem, but there's negatives on the left side.
Okay, right. What about this point right there, for example? Does that point make sense on the red curve? Because we can see that goes through the origin. When x is 0, the value of the derivative function is 0. Right? The Maverick chicken, do you see something there? Connection between those?
Not yet.
Not yet? Anybody got a connection? Why must the value of the red function be 0 at x equals 0?
Because it's 0, 3, that's the only place where the tangent lines are 0.
Exactly. Okay, good, because the value of the derivative function is equal to the slope of the original function, right? So the value of the derivative function at x equals 0, we can see, has to be 0, because that's where the original function has 0 slope, right? Where its tangent is horizontal, right? As I move further to the right along the blue function, it's getting steeper, isn't it? Right? It's getting steeper, so what is that saying about the value of its slope as we move to the right? It's getting bigger in a positive sense, right? Okay. What is the value of the red function doing? Well, it's getting bigger as we move to the right. Everybody see that? Okay. If we move to the left along the blue function, as we progress to the left, the slope is getting increasingly negative, right? That's what the value of the red function is. Agreed? Okay. I'm going to put up 2 more functions here. I'm not going to go through the exercise of actually taking this derivative. You guys will get plenty of practice with that on the assignment, but I want to see if you can, if it makes sense that the blue function is going to be the function and the red function is going to be the derivative, if you can make the connection between these two.
Something we do with See what that K is, it's like. Oh, cause I need to go to the. Classes. Yeah, no, it should be like, I can't remember.
Okay. So this, blue function is f of x, red function is f prime of x. Does that make sense?
Yes.
Okay, tell me how come. Actually, let me do one other thing to this. Just I could make this a little bit better. One slight change here. Let's make this. There. Blue original, red derivative. Somebody tell me, pick a point on both curves and tell me why they have to be the way they are.
Is 0 too obvious?
Okay? So once again, if we pick x equals 0, what's the slope of the blue function at x equals 0 if I drew a tangent line? 0. It's horizontal, isn't it? It's horizontal tangent. So then the value of the derivative function must be 0. Okay? What's the blue function doing as we scoot to the right along the function? It's going up, isn't it? It's going up. This time it's a little different, isn't it, though? It starts off, it moves up slowly, and as we move further to the right, the slope appears to be increasing more and more rapidly, right? And so you can see on the red function, that's sort of what's happening here. As we move to the right, we can see that the value is increasing slowly at first, but as we move along, it starts to increase more and more rapidly, right? Does that make sense? But that's even a step beyond what we have to do. Really, at this point, all I really am concerned that you see is that as the ant walks to the right on the blue function, his slope is increasing, right? So therefore, as we move right on the derivative function, the value must be getting more positive. Okay, what about if the ant moves to the left on the blue function? What's happening to the slope of the curve? It's not dropping. It's actually increasing, isn't it? As we scoot to the left, look at the tangent lines that we're creating, right? Look at these tangents. Like, there's the tangent. Scoot back a little bit, it's slightly positive. If I go back more to the left, it's more positive. More to the left, it's more positive. As I scoot to the left, the slope is actually getting more and more positive, isn't it? Right? Well, look what the red function does. That. See what I'm saying? The red function, as I scoot to the left, its value is getting more positive. Once again, this is kind of a tricky connection to make at first, but the value of a derivative function has to correlate to the slope of the original function, right? So where the slope of the original function is large and positive, the value of the derivative function would have to be large and positive. Yeah. Okay. Right. Whenever we talk about the value of a function, we're talking about the y value, right? Make sense? Okay, so then if I wanted to, for example, I'm going to give you a function, and I want you to draw the derivative. Okay, so how about if we do something like this? Blue is original. what should my derivative function look like? What should its starting value be?
It's gonna be through
It's
origin.
gonna be low.
What should the starting value be?
It's
Should be 0, yeah, shouldn't it? Because look at the original, if I look at a tangent line, well, it's supposed to be. If I look at a tangent line right there, it's horizontal, right? What about over here, what's it gonna be? Negative. If I go further down, more negative, right? Okay, so then 0, negative, more negative, right? So maybe initially it just looks like that. Everybody agree? I mean, it's not an exact science here, but you get the idea, right? Okay, what's it doing from there to there?
Consistent. Or
It's-
actually, it's staying the same, so it's just. flat.
Saying the same slope, right? So then what should my graph down here do between those x values,
Not changed.
right? Okay, what's it do from there to there? Positive,
But
right?
doesn't it jump to positive?
So it's gonna jump, yeah, how about that? So it's gonna jump up to here, isn't it? Right? Okay,
And
now,
Just a straight line.
it's a straight line. Okay, make sense?
So, this is what we did with the reading velocities last year.
It is, right?
The derivative based off
We
of
don't
the
know
slope.
that.
Say it again?
The derivative is based off the slope of the tangent.
Exactly, yeah, okay. Now, there's one little trick here that, what do we do at this endpoint?
Yeah.
What do we do at this endpoint? I mean, that's a problem, isn't it? Because how can the derivative go from this value? It can't overlap vertically, right? Everybody agree? So then, what would I have to do, do you suppose? And we'll talk more about why this is the case later, but here's one approach to it. What do you think we'd have to do at this endpoint? Because I can't do this, because they can't overlap vertically. So maybe suggestions. What can I do to these endpoints?
You can't draw.
A hole? Okay, so say I put a hole there. Could I, what would happen there?
Hole.
Hole? Okay, it would kind of have to be, wouldn't it? Because what if you thought, well, let's just make that one a solid dot. How do you choose? You see that? How do you choose which one would get the solid dot and which one would get the hole? You see what I'm saying? It makes no sense, does it? There shouldn't be any preference, right? These are both just line segments. And so when you get something like that happening, you could kind of say, okay, there needs to be a certain isotropy. There can't be,
Well, isn't there there is an infinite number of tangents at that point, is there not?
right, which is the other way to look at this. So you can see that this has to be an open circle, right? Because there shouldn't be any preference for the left or right. And furthermore, how could you even define a slope there, right? Isn't the slope by definition, that's gotta be based on the relationship to the adjacent points? Everybody agree? Okay, because if I focus in, if I zoom in and zoom in and zoom in, like around that point right there, well, the curvature is gonna tend to, as we zoom in, and the points, would you agree the curvature is gonna flatten out? And so relative to its adjacent points, it's gonna start to look more like a line, isn't it, right? But if I zoom in on that point right there, does it ever look any different? It never looks any different, does it? It always looks like exactly like that V, doesn't it? Right? And so I can't ever get to a point where I can state that there's a given slope with this, that there's gonna be a tangent line that's gonna match this, because it'll never happen. It's always gonna be a V, right? So what it means is, can I even define a slope at that point? I can't. And so the derivative has to have a hole. There has to be a hole in the derivative function because it can't do its job, right? It can't define a slope of a tangent line. Okay, so one of the things we're gonna find, and we'll discuss this more, real soon, is that this is one of the kinds of places where a derivative function can't exist at a sharp corner. Okay? Right? That make sense? Okay, let's try another one. Okay, so here's the original. No,
Okay,
no, you wouldn't.
sweet. At least I know I don't need to, or I should. But I don't have to know it right now, or like I shouldn't be expected to know it right now.
Okay, there it is. There's the function.
The original function?
Yep. I want the derivative.
Alright, so it stays 0, and then it goes up, and then it goes.
So our ants have evolved. They've evolved the ability, our calculus ants, not only to be able to sense their position on the XY
Are
plane.
these be mice?
They now, the genetically modified ants can actually sense their slope as well. So their slope sensor, as this ant is walking along, is reading what? 0. What's it reading down here?
0.
Okay, so then it looks so far, and then when we get to this point right here, the slope sensor goes haywire, right?
Anthony Dolan
So
to
we
the
know we're gonna
office,
get an open
please.
circle
Anthony
there,
Dolan
right?
to the office.
Question is, what happens there?
Oh, tears. No, yeah, just
What's gonna happen there and
What's
why?
happened to her?
get in the middle.
So right here, at this point,
Yeah, cause there's no way you're gonna find it.
Would it still
So it'd just be a hole, wouldn't it?
would it be knowable because there's no change in slope?
there's no change in slope, you're right, except, remember what we said,
It's
the
based
slope
off
has
of
to be
the adjacent
defined
points.
by the relationship to the adjacent points.
And it has to be points plural.
Wouldn't it be a negative hole down by itself?
And so it's gonna be what?
Wouldn't it be like a hole by itself, negative?
It turns out it's gonna be like this.
Oh, damn it.
Just right.
It's gonna be like this, because,
Okay.
and here's why. Because as you're at that end point, your next step takes you to there, right? So, approaching from the left, it looks like that's gonna be an infinite slope. Approaching from the right, though, you see a horizontal slope, don't you? See what I'm saying?
Yeah.
Well, they're different. So which one's right? Well, they can't both be right or both be wrong. Right? And so once again, we're gonna get an open circle there. Now, this will be easy for us in a couple days because this is another type of place where we are just gonna know that a derivative function can't exist. Right? It can't exist when there's a break in the function. Okay? So we got sharp corners and breaks. Real quick, what's he gonna do here?
Oh,
Go to lunch.
Yep, and then what about right here?
got
Down,
curve,
down.
pop.
Nope, go negative curve.
Okay.
Okay, more.
Everybody agree?
Okay.
Yeah.
Yeah.
Okay. All right, go to
So,
lunch.
just terrible, who should it be by? So I was thinking Trump, would that be weird? Calendar?
Wait.
Just able, terrible, like terrible.
It's like that.
Oh, yeah.
Mexican review 101.
This is the stuff we did today, we did the lawsuits
No,
last year.
Yes,
and
it
I
is.
understand it.
The tamales.
Yes,
Nope.
it is. You're gonna have some real insight into this, because you've already seen it physics. How do you see why those calculus type lessons are so exciting?
Yes. I never understood how they were reading the graphs.
Yeah.